Yes, some of them do believe in a cyclical universe, and the Big Bang is an event that occurred approximately 60 years ago when space became extremely hot, dense, and packed with particles. The Big Bang theory has remained the most successful explanation for our cosmic origins, explaining how the universe began as hot, dense, and radiation-rich matter expanded, cooled, and gravitated ever since. This process created protons and neutrons, the first light elements, stable atoms, stars, galaxies, planets, and intricate chemistry that some 13.8 billion years later could give rise to life. The universe is still expanding, and we are trying to figure out exactly where it came from and how it came to be the way it is today. However, the more we investigate, the more the Big Bang theory fractures the idea that the universe emerged out of nothing, which is why many scientists, including renowned physicist Brian Cox, vehemently reject it. The Big Bang theory faces growing challenges as the James Webb Space Telescope, the most potent space telescope ever, gathers very compelling evidence that suggests the Big Bang wasn't actually the beginning of everything. This begs the question of what existed before the Big Bang, and if it wasn't the beginning, then what was? Stay tuned today as we shed some new light on the origin of the universe in today's episode of I200M. The first time the phrase the Big Bang was uttered was over 20 years after the idea was first described. Ironically, the term itself comes from one of the theory's greatest detractors, Fred Hoyle, who was such a staunch advocate of the rival idea of a steady-state cosmology. In 1949, he appeared on BBC Radio and advocated for what he called the perfect cosmological principle, the notion that the universe was homogeneous in both space and time, meaning that any observer, not only anywhere but at any time, would perceive the universe to be in the same cosmic state. He went on to deride the opposing notion as a hypothesis that all matter of the universe was created in one Big Bang at a particular time in the remote past, which he then called irrational and claimed to be outside science. But I'm afraid I don't really believe in the Big Bang. The idea, in its original form, wasn't simply that all the universe's matter was created in one moment. The idea that the universe, not just the matter contained within it, had emerged from a state of non-being in the finite past was initially mocked by Hall, but it had already changed from its original meaning. As absurd as it may sound, this idea was an inevitable but difficult to accept byproduct of Einstein's new theory of gravity, general relativity, which he proposed back in 1915. When Einstein first cooked up the general theory of relativity, our concept of gravity forever shifted from the prevailing notion of Newtonian gravity. Under Newton's laws, the way gravitation worked was that any and all masses in the universe exerted a force on one another instantaneously across space in direct proportion to the product of their masses and inversely proportional to the square of the distance between them. But in the aftermath of his discovery of special relativity, Einstein and many others quickly recognized that there was no such thing as a universally applicable definition of what distance was or even what instantaneously meant with respect to two different locations. With the introduction of Einstein's relativity, the notion that observers in different frames of reference would all have their own unique, equally valid perspectives on what distances between objects were and how the passage of time worked, it was only almost immediate that the previous absolute concepts of space and time were woven together into a single fabric, space-time. All objects in the universe move through this fabric, and the task for the novel theory of gravity would be to explain how not just masses, but all forms of energy shape this fabric that underpins the universe itself. Although the laws that governed how gravitation worked in our universe were put forth in 1915, the critical information about how our universe was structured had not yet come in. While some astronomers favored the notion that many objects in the sky were actually island universes that were located well outside the Milky Way galaxy, most astronomers at the time thought that the Milky Way galaxy represented the full extent of the universe. The reason Einstein added a cosmological constant, a special kind of fudge factor, to his equations, even though it was mathematically permissible, was because, in the absence of one, the laws of general relativity would guarantee that a universe with uniformly distributed matter, as concrete predictions about the universe. Over the 1960s and 1970s, as well as ever since, a combination of observational and theoretical advances unequivocally demonstrated the success of the Big Bang in describing our universe and predicting its properties. 1. The discovery of the cosmic microwave background and the subsequent measurement of its temperature and the blackbody nature of its spectrum eliminated alternate theories such as the steady-state model. 2. The the measured abundances of the light elements throughout the universe verified the predictions of Big Bang nucleosynthesis while also demonstrating the need for fusion in stars to provide the heavy elements in our cosmos. 3. The farther away we look in space, the less grown-up and evolved galaxies and stellar populations appear to be, while the largest-scale structures, like galaxy groups and clusters, are less rich and abundant the farther back we look. The Big Bang is verified by our observations. It accurately and precisely describes the emergence of our universe from a hot, dense, almost perfectly uniform early stage. But there are questions it simply doesn't address. What set up the initial conditions that our universe started off with? Why is the universe so much more uniform and isotropic than the laws of physics predict it should be? Why does the universe exhibit the same temperature and density everywhere we look, even in regions that are causally disconnected from one another? What brought about the initial expansion rate that precisely balances the different forms of energy present in the universe? And why are there no leftover high-energy relics, such as magnetic monopoles, black hole remnants, or other exotic objects, in the universe today? This is why the Big Bang, despite its name, isn't the beginning of the universe. It doesn't address the true beginning. Instead, the way that science explains the beginning of the universe is through something more modern, the theory of cosmic inflation. The universe, instead of emerging from an arbitrarily hot, dense state, instead emerged from a state where all the energy that would go into the universe was inherent to space itself. And that state possessed a very large positive energy density, one that caused space to expand at a constant, exponential rate. That inflationary state dilated the universe to enormous scales, stretched it to be spatially flat, smoothed it out to be isotropic and homogeneous, and created a density that was identical everywhere. It was only when inflation ended, when that inherent energy was transferred into particles, antiparticles, and radiation, that what we know is the hot Big Bang actually began. The universe today, 13.8 billion years later, is just an evolved, aged version of that initial hot, dense state. The Big Bang no longer means what it was originally supposed to, the birth of space, time, and the universe itself. But instead, it refers to the beginning of our universe as we know it, including the laws of physics that we recognize and the start of the hot, dense state that has expanded, cooled, and gravitated ever since. With the 2010s now behind us, what will the 2020s bring as far as revolutionizing our understanding of the universe is concerned? While that's a mystery to everyone, it also has the potential to be the best decade for cosmology in the history of the science. Stay tuned, and be ready for what might be the best decade yet in discovering our cosmic origins. Ours would be unstable against gravitational collapse. Einstein sided with this latter viewpoint and believed the universe was static and eternal. This early story that Einstein and others had told themselves in 1922 would quickly change thanks to two developments, one theoretical and the other observational. In reality, it was very simple to demonstrate that any initially uniform distribution of motionless matter, regardless of shape or size, would inevitably collapse into a singular state under its own gravitational pull. By adding this extra term of the cosmological constant, Einstein could tune it so that it would balance out the inward pull of gravity by figuratively pushing the universe out with an equal and opposing action. After completely figuring out the equations governing an isotropically and homogeneously identical universe filled with all kinds of matter, radiation, and other forms of energy, Alexander Friedmann discovered that such a universe could never remain static, not even in the presence of a cosmological constant, and that it would always expand or contract based on the details of its initial conditions. Edwin Hubble was the first to discover in 1923 that the spiral nebulae in our heavens were located far beyond the Milky Way galaxy, which contained no items that might have jeopardized our home galaxy. As Vesto Slipher had previously noted, the spirals and ellipticals discovered across the cosmos were actually their own island universes that are now known as galaxies. Furthermore, the vast majority of them appeared to be traveling away from us at amazing rates. In 1927, the universe must have expanded to its current state from a single point of origin, which he called either the cosmic egg or the prime-val atom. This was the original idea behind what would eventually become the modern theory of the Big Bang. Georges Lemaitre was the first to put these pieces of information together, realizing that the universe is expanding today, and that if things are getting farther apart and less dense today, then they must have been closer together and denser in the past. The idea that the universe had a beginning or a day without yesterday was not, however, generally accepted for some time. Lemaitre originally sent his ideas to Einstein, who infamously dismissed Lemaitre's work by responding, "Your calculations are correct, but your physics is abominable." Despite the resistance to his ideas, however, Lemaitre would be vindicated by further observations of the universe. Many more galaxies would have their distances and redshifts measured, leading to the overwhelming conclusion that the universe was and still is expanding equally and uniformly in all directions on large cosmic scales. In the 1930s, Einstein conceded, referring to his introduction of the cosmological constant in an attempt to keep the universe static as his greatest blunder. However, the next great development in formulating what we know as the Big Bang wouldn't come until the 1940s, when George Gamow, perhaps not so coincidentally an advisee of Alexander Friedmann, came along. In a remarkable leap forward, he recognized that the universe was not only full of matter but also radiation, and that radiation evolved somewhat differently from matter in an expanding universe. Gamow used this information to make three excellent general predictions about the early universe. 1. At some point, the radiation from the universe was hot enough for a quantum of radiation to have ionized every neutral atom, and that this residual radiation bath should continue to exist today at a temperature only slightly above absolute zero. 2. At some even earlier point, the radiation would have been too hot to even form stable atomic nuclei, and so an earlier stage of nuclear fusion should have occurred, where an initial mix of protons and neutrons should have fused together to create an initial set of atomic nuclei, an abundance of elements that predates the formation of atoms. 3. Finally, this means that there would be some point in the universe's history after atoms had formed where gravitation pulled this matter together into clumps, leading to the formation of stars and galaxies. These three major points, along with the already observed expansion of the universe, form what we know today as the four cornerstones of the Big Bang. Although one was still free to extrapolate the universe back to an arbitrarily small, dense state, even to a singularity if you're daring enough to do so, that was no longer part of the Big Bang theory that had any predictive power. Instead, it was the emergence of the universe from a hot, dense state that led to our